Okay, let's continue our lecture. I think during the break, some people asked me what exactly common filter really is, why, how to connect to real world examples. So far, we are only dealing with probabilities. So the way we are doing this now is we're trying to lay down the foundation first, really solid. Then we give you plenty of examples. In product 3, you're going to use common filter to estimate the robot I think pose or location. And so typically common filter is most very popular is because of robotics and autonomy. I think that's one of the main reasons recently, especially autonomous vehicles. So we are talking about estimate X. What typically X is like your position, location, or even orientation of your vehicle. And the measurement could be your GPS measurement. And also your measurement could be your onboard IMU measurement. And those are all giving you information about where you are and how fast you're traveling. Those are your state, but those has noise, okay? You should cleverly combine those measurements to have an accurate estimate of your car's position. And if you really do autonomous driving level 4, level 5, you need to know, you have a high definition of maps, like a SLAM, and you have somehow additional measurement, like a locally align your point cloud with your map point cloud that give you other corrections. So you fuse all of this measurement information, those are all your Y. Okay, your Y is something like a point cloud that taking in, and a GPS signal, and IMU measurement. And your X is the hidden variable that you're trying to estimate, is your exact location. It may possibly involve your orientation. And their speed, their velocity is also sometimes state. Okay, so you're using those information to estimate the position or orientation and their velocities. That's one typical use of common filter. Okay, you don't have to, nowadays you don't have to use common filter, but common filter definitely give you a starting point to understand those things. Okay, let's go back. I think we'll give you examples later on, but for now, I want you to truly understand the foundations, the math, and the fundamental nature. Fundamentally, common filter or the minimum mean square estimate is just trying to compute conditional expectation. As I mentioned before the end of the last lecture, it's very hard to compute. I'm not sure whether you can, you have done this before or not. If I ask you to integrate a function in 10-dimensional space, if you don't have a closed form solution, it will be really hard. How do you integrate some function, very complicated function? You typically grading the space into small cubes or cells. It's like a finite element method, right? So you somehow divide into this, and assuming within this of this, the function value doesn't change that much, then you sum over them. It's like, but as the dimension grows, those number of cubes becomes larger and larger. It grows exponentially with the dimension. So once you reach 5 or 6, it's really hard. It's extremely hard. It's almost impossible. And but there's a catch. There's one exception, which is Gaussian. Okay, that's why Gaussian random vector is so important. If X and Y are jointly Gaussian random vectors, Gaussian is not a variable now, it's a vector, okay? They could be, this could be Rn, this could be Rm. Okay, if they're joint Gaussian random vectors, I'm going to define what they are, what joint Gaussian means. Then there is a simple analytical form for the conditional expectation. So you don't need to go over this integration. They have a closed form solution. That's the exception. That's why Kalman filter or why Gaussian vectors are so important for estimation or learning problems. Okay, as Yuntian said, in machine learning, the first part of few lectures all about Gaussian vectors, random vectors. So now let's give a review of Gaussian or normal distribution. You have learned normal distribution for sure, okay? The density function looks like this. Can anyone explain why this is called Gaussian? What's special about this? Okay, that's the least part. Okay, good. Central limit theorem tells me that summation of a large number of independent random variables eventually distributed according to Gaussian. Okay, but that's a property of Gaussian.
Maybe Gaussian is already has something with the least problem that if the error is distributed Gaussian, the least problem is the solution.
Yeah. Well, there's a lot of story behind the definition of Gaussian random variables or densities. I want to tell you is that there's nothing special about this, okay? And you can have your whatever Shu-Yan's distribution. I can say not exponential, I can say this is 10 raised to the power of this. Of course, you need to rescale it so that integrate, but the density function you have to integrate it to 1, right? So you have to make sure the constant is right. But that can be called Shu-Yan's distribution. It's whatever it is, it's just something artificially imposed. Okay, I don't think in real world there's any kind of real distribution are exactly Gaussian. The reason this form is useful is due to many reasons. But one of the reasons is that it's very kind of good for us to compute conditional expectations. Okay, and of course the main reason is because of central limit theorem. So let's review. So these are few normal distribution in R1. My question is that suppose this is normal of mu1 and sigma 1. This guy is normal of mu2, sigma 2. Mu1 and mu2 seem to be both 0. I want to ask you which sigma is bigger. Sigma 2 is bigger than sigma 1, right? The variance is larger, so it's more, the density is more diffused. Okay, and how do I know? I can say, okay, I will say, I can give you a random variable. I ask you whether it's Gaussian or not. How do you check?
What do I know about the random?
You can, well, what do you need to know in order to prove or check it is Gaussian? You just need to know anything, okay? Any random variable, all you need to know is the density function or the PMS. If you want to prove one variable is Gaussian, you have to show its density function or PDF have exactly this form. It could be having different mu and sigma, but it has to be written as this form. Are you with me? If I like a Shu-Yan's distribution, then that's fine. You need to check whether it's of this form. It could be, right? So that's 1D, and you need to make sure that this guy integrate should be 1. Okay, so that's where this weird form of constant come from, right? You need to make sure this is a constant, right? You need to make sure the constant times this integrate out to 1. Then I'm not sure how many of you have seen n-dimensional Gaussian random vector. it's same. It has a mean or expectation, but also have a covariance matrix now. Okay, so in 2D, it looks like this. That's two-dimensional Gaussian distribution. So exactly have this form. You can define your own form, okay? But everyone agrees this form somehow it has a lot of nice properties, so we somehow use it as much as we can to represent practical distributions. The first of all is that this is also exponential. This guy, this is the covariance matrix of the Gaussian random vector, and this guy is almost like what? It's almost like X transpose times a matrix P times X, right? It's a quadratic form that we reviewed, at least in my online video lecture, there's review on those quadratic forms. And if you look at this quadratic form is this number, okay? If you look at this level set, or let's say less than 1, for example, this will be a the ellipsoid. It's an ellipsoid, okay? This is the ellipsoid. That's why if you cut this, and the level set will be ellipsoid. So you also need to multiply by this kind of weird-looking formula. This is a determinant of the covariance matrix, and why we have this constant is we need to make sure the integration of this density function over the entire Rn is 1. That makes the density function a valid density function, okay? So if n is 1, then this becomes this formula. So if I want to check, you just need to know this form, okay? If I want to say whether a vector is Gaussian or not, you just need to check whether its density is of this form or not. In practice, it's very few of them has this form, but if you assume some random variable of this form, then you can create many of Gaussian variables that also have this form. Again, so there's nothing mysterious about those density formulas. You can define your own formulas. Okay, but let's stick to this Gaussian. If you want to check something is Gaussian 1D or ND, you just need to check the density function. Okay. All right. There are a few properties, as I mentioned, are very important or special about the Gaussian random vectors. And first of all, it's very simple to represent. If I say, suppose your distribution of your grades in the midterm, maybe it's we have a lot of full marks, right? Anyway, let's not talk about our grade. So typically you think your grade may be something like this distribution, all right? But in reality, oftentimes it's like that, okay? Some good students are really good, and there's somehow 2 peaks, okay? And if you want to represent those distribution, in 1D it's easy, right? You just use somehow like a histogram, right? Its value, you can represent this curve very easily. But in high dimension, if you want to represent this very weirdly looking function, it's very hard, right? You need to have a big table to store all their values if there is no analytical form. But for Gaussian, it's very simple. The form is simple. It's only represented or characterized by mean and covariance matrix. Let me repeat. If I say something is Gaussian, all you need to know is the mean and covariance. This is the vector, this is the matrix. If I know these 2 things, then I know exactly the density. In other words, the density are characterized by 2 parameters. One is the mean, the other one is covariance. Okay, so we don't need to store the entire values of this multidimensional function. Okay, I have an analytical form of the function that are parameterized by mean vector, and the covariance matrix. The second fact, the first fact, this is a property. The first fact is uncorrelated joint Gaussian vectors are independent. What does uncorrelated mean? So it means covariance x and y is 0. They're uncorrelated, so the covariance is 0. Typically, it doesn't mean they're random, independent. But in Gaussian, that means what? X are independent of y. What does this mean? fxy, the joint distribution equals the marginal multiplied by each other. Okay, uncorrelation means independence. That's a special case, property for Gaussian. Can you prove this, Shuyan? How do you prove it? You're asking me or you're answering me the question? By definition, of course, you just need to check. It's very simple to prove. I want you to make sure it is simple to prove. Do you feel that or not?
No.
If I write it down, it take another 10 minutes. I think everyone will agree. This is very simple to prove. But it's, well, let's say conceptually simple, but it's tedious. Okay, you need to do a lot of algebra and to factor things out. But that's fine, it's conceptually simple. You just need, how do we prove this? You just assume their covariance is 0, then you check its density, and you find it out, oh, the density can be written as 2 marginal multiplied together. That's it, that's the proof. And you can go over the steps, you find it out. I don't need you to prove, but at least I need you to know what it takes to get its proof done. Okay. The second one is even more important for Kalman filtering. It's linear transformation of Gaussian is Gaussian. So if I say x is Gaussian, there's a mu x, sigma x. Okay. Then I would say there's another number, let's say 2 of x plus b is a linear transformation of x, right? 2x plus 3, let's say that. In scalar case. Then I can conclude G is also Gaussian. How to prove this? Shuyan. How to prove this by definition? How to check G is Gaussian or not? Density function, then you do matching to see whether it is satisfy the form of Gaussian. If this is Gaussian, that's our assumption, you can compute the density of G, and then you will realize, oh, it is still Gaussian, because the density is of Gaussian form, maybe with a different mean and covariance. It has different parameter, but it's same form of the Gaussian variables, okay? If you want to check, you have to find the density function. But this is conclusion, whatever linear transformation you have, the result is also a Gaussian. The third one, I will do 10,000 emphasize all those. It is conditional Gaussian is Gaussian. That's exactly the Kalman filter based upon, okay? That's the fact Kalman filter based upon. Conditional Gaussian is Gaussian. I'm not sure how much you can understand that. We will check this. Okay, we'll cover this part in detail, hopefully today. All right, let's go over a little bit depth, go into the depth of each of these facts. First of all, fact 1. So let's say x and y are jointly Gaussian. I need to formally define this term for you. If you so let me say jointly Gaussian, I will say by definition means what? Means x, y as a whole vector. Let's say as a whole vector. Is a multidimensional Gaussian. It's Gaussian. If I put them together as a bigger vector, this vector is a Gaussian random vector. Okay. In other words, suppose x is Rm. This is in Rn plus m, right? X is Rn, y is Rm. That means x and y jointly distributed as a Gaussian with some mean vector and some covariance matrix. Okay, so if these two are jointly Gaussian, then I can say these two independent or not. You only need to check this one of the facts. Okay, covariance is equal to 0. Okay, covariance 0 if and only if it is independent. X and y are independent if and only if their covariance is 0 for Gaussian only. However, this is something I think it's optional for maybe advanced student. I may upload some notes to explain. It could be possible x and y are both Gaussians, but they are not jointly Gaussian. Let me repeat. If x and y could be, each of them are low-dimensional Gaussians, but if you put them together as a vector, it's not Gaussian anymore. It's very possible. I will give an example, maybe upload a note to this. This will take some effort to explain. So the question is, another fact, this is fact 1.1, is if x and y are both Gaussian, and x are independent of y, then x and y are jointly Gaussian. Both Gaussian means each of them are Gaussian. If you put them together as a vector, you have to specify the joint distribution. Okay, given the margin nodes, only given the margin node doesn't fully specify the joint. I hope you can somehow understand that. Given two random vectors, the complete information you need is the joint distribution, right? But if I only give you two margin nodes, you don't know the joint. Okay, you cannot fully know the joint. Okay. So it's possible each of these margin nodes are Gaussians. If you put them together, there's cases that it's not a Gaussian vector anymore. But if these two are independent, the construction is Gaussian. All right, this fact somehow is useful, but I don't need you to fully kind of understand this. All right. All you need to know is that if x and y are jointly Gaussian, then independence means covariance is 0 or uncorrelated. The second one is affine transformation of Gaussian is still Gaussian. So let's say x and y. Oh, do I have y? No. All right. X is Gaussian. This is a matrix. And these are deterministic matrix. This is deterministic. Then I define another variable, and this variable is a affine transformation. Do you know what affine is? 仿射, okay. So if I don't have this B, then that's linear. Okay, if I have this B, in a more rigorous way, we call it affine, but you can also loosely call it a linear as well. Okay, it's a linear function or affine function of x. If I can define this way, then Z is also Gaussian, which means this is mu of Z, right? It's A times mu times B plus B, and this is mu of Z. This is the covariance of Z. Actually, you can derive this right away, right? Because mu of Z is expectation of AX plus B. And we know the property of expectation as expectation times A times mu plus B. So that's mu of Z, right? And the covariance of Z is what? Covariance of Z with itself. AX plus B, AX plus B. But you know this plus B doesn't make any contribution. That's our property of covariance, right? That become A sigma A transpose. As long as I know, but this doesn't tell me anything about the distribution, the PDF of Z. It only tell me the mean and covariance. The fact is that this Z I know will always be Gaussian. That's a fact. If you want to check that, you need to find the density function of Z, and you will realize it will be a Gaussian. Okay. This can be used to test whether a random variable is Gaussian or not. So now I'm going to ask you, Suyuan. This example, I have a R3 random vector. I call it Gaussian. Then I'm asking you, this is jointly Gaussian, right? X1, X3, X2, X3 is jointly Gaussian. Because I put them together, it is a Gaussian random vector. Now I'm going to ask you, is X2 a Gaussian? By definition, I didn't ask you to prove, okay? But by definition, if I want to know whether this is Gaussian or not, what I need to do? I need to find the margin nodes for X2. Okay? I have the joint, so I know the margin nodes. Or I know how to compute the margin nodes, right? So will be I need to integrate out X1 and X3 for the joint. Okay, X1, X2, X3, and dx1 and dx3. That will give me my margin nodes for X2. If I was able to somehow good enough in calculus to find it out, which I don't, I cannot. I don't know, I forgot quite a bit about those formulas for multivariable calculus. But conceptually, you can do this, okay? By plugging in the joint density for this X vector, and you will find out this will be a Gaussian or not, okay? But we don't do this, right? Can you tell me a shortcut by the fact we introduce here, this is Gaussian or not, X2? So I will say X2 is equal to 0, 1, 0 times X1, X2, X3 plus 0, okay? Can I write this, okay? Your linear algebra should be good enough for you to see it right away. Is that right? So it is a linear or affine this is linear linear function of X. And X is Gaussian, so X2 is Gaussian. So I don't need to do the integration. Okay, I can use the fact too to directly claim, okay, this is, I would say this is a affine transformation of X. So Gaussian. We're done, all right? So that's Gaussian. Now you see the fact. Is this a Gaussian? Shuyan, you're laugh. Is this Gaussian? Why? A3. Okay, so this is a finite transformation again. It's Gaussian. Are you with me? Can you check by definition? Yes, you can do integration. Now what I'm asking is this Y Gaussian? Y, can you write down a linear transformation to define Y in terms of X? What is it? 1, 0, 0, 0, 0, 1 times X. Okay? So you see this is also Gaussian. So the third one question that I ask you is x2 independent of x1? Is x2 independent of x1? Where's the covariance? I need to check. Basically, I can only well for Gaussian I only need to check this guy, right? What is it? X2, x1 is the second row, first column. It's 0. So covariance is 0. So x2 independent of x1. Covariance 0 implies independence, but only for jointly Gaussian. Okay, what about x1 and x3? Covariance of x1 with x3 is -1. So it's -1. No, it's not. Sorry, not independent. Okay, not independent. Any questions? So we are trying to use those facts. Okay, here we come to the most challenging part and the most important part for Gaussian random vectors, which is the third fact: conditional Gaussian is Gaussian. Okay, the fact formally states like the following: conditional Gaussian is Gaussian. That's the short notation or short summary of the fact. Precisely what I mean is that let X and Y be jointly Gaussian. What does jointly Gaussian mean again? I put them together. It's a joint Gaussian random vector in Rn plus M. Okay, and I can partition their covariance matrix in this form. I'm not sure whether you can see that or not. I can give you examples. Suppose I have Z1, Z2, Z3. That's these are a random vector, okay? This may have the meaning of Shenzhen temperature. This is Guangzhou, okay? This is Beijing. Okay? I can partition in any way I want. Okay? I can say this is my X, this is my Y, that's fine, right? I can define this in different dimensions. Then in this case, X is R2, Y is R1. And they could be jointly Gaussian. You see what I mean? They can jointly Gaussian. So the conclusion is that the conditional distribution of x given y is Gaussian. Although I have explained this many times, I want to write it down again so that you can think, not only memorizing the formulas. So xy are jointly Gaussian. Okay, so we'll have a density function, right? The jointly Gaussian means this density function has the Gaussian form. Okay, right? So now I will say, what do I mean by conditional Gaussian is Gaussian? So given, let's say given y, capital Y equal to y, maybe Beijing temperature equal to 0 degree, given that fact, x is still random. Are you with me? X is still random. Given Beijing is 0 degree, doesn't fully specify what Shenzhen and Guangzhou already is. Okay, x is still random. Its distribution, its density will be what? X given y, capital X, small x given small y. Okay, so this capital Y equal to small y, that means Beijing equal to 0 degree. X is still random. I can find the conditional density. Any random variable have a density, right? It's still uncertain. I know this density is this, and we can show this density is a Gaussian. That's all it means. These three vectors, these three variables, when I specify z equal to a fixed number, I can find the conditional density of x given y. And that density function, it turned out to be also in a Gaussian form. That's what I mean by conditional Gaussian is Gaussian. If you check anything is Gaussian or not, you just need to check its density function, whether it is in the form of Gaussian or not. Okay, I hope that's fine, right? So then this become a few formulas, and which you can derive by hand, or you just somehow remember them. These are the few formulas that I remember in my life. So whenever you ask me, I know those formulas. I think we are open note exams for the final, right? So you don't have to memorize anything, but these are so important that somehow I got memorized. I remember them whenever you ask me. Okay, so you can compute this density. It turns out this density of Gaussian form. Gaussian form is characterized by two parameters. One is mean, the other one is covariance. Okay, and we have a formula of this conditional mean and conditional covariance in relation to the previous marginal mean and the joint covariance. Okay, so the form, it looks like follows. I just want to give you how I understand this form. For example, this mu of x is expectation of x. Okay, and this is expectation of y. Okay, this is given, that means a realization of y. given capital Y equal to small y, right? Those are covariance matrices. So, but it makes sense or not to you? I'm not sure. It makes perfect sense to me. I don't want to read this, but I want to explain this to you. When I know, always think about Guangzhou and Shenzhen, okay? In this class, we're in the Bay Area here, okay? So this is what on average you expect to see Y. Maybe the average temperature of Guangzhou is 25, okay? Today, you find out Guangzhou is 30. And this term will be a surprise term. This is what I call a surprise. If it is 0, no surprise. Today's temperature is the same as the average. If it is 30, this is 25 on average, then there's a 5 degrees surprise. Okay, today is hotter than I expect. How does Y's surprise on Y got translate to your belief about X? So I know X typically about this, right? That's on average. Today I know Guangzhou is above its average. If we are positive correlated, that means I will somehow have a surprise effect got added up to the expectation of X as well, okay? Now this term, inverse of Y, is typically, I would say this is how noisy Y measurement is. Measurement is, okay? How noisy. The larger covariance, the more noisy, the less weight you want to put on the measurement. You see what I mean? It's too noisy. So sometimes give you 30, sometimes give you 0. So you wouldn't trust that much, okay? You somehow divide it. And this guy is the correlation between X and Y. So how much Y above the mean will got translated to X above its mean. Okay, so typically, so this formula is, I think you need to somehow have a sense what it is, right? Expectation times covariance X, Y, and how, divided by noisiness, and times the surprise term. And this is the covariance minus CY. This we use less, okay? At least this part is to have understanding. So if you derive them by doing this, this is what? The joint divided by marginal, right? You can compute this. If you compute, you find out this Gaussian and its mean is covariance like this. So you can compute this, all right? I encourage you to do this. I think it will take a day or two for you. If for vector-wise. If for 2 random variables, I think maybe you have done this in your introductory probability class. I think so. You should. Okay. Now let's accept this fact. Let's do some exercise. At least use some. Now suppose X and Y, X is R2, Y is R, and Z is jointly Gaussian. So I want you to say, can you compute the minimum mean square estimate given capital Y equal to, sorry, let's do something different. Let's this, Y is 2. Okay, the reason is that makes things fun. So this is my X part, this is my Y part, okay? I divide into these 2 parts. Okay, so I want you to say, what if I observe these 2 values of Y, what's the best estimate of X given Y equal to this? Now become estimation theory. The result we learned so far is that, okay, the minimum mean square estimate, this is our small y, right? Mean square estimate is conditional expectation. Okay. So first of all, I know x and y jointly Gaussian. Do we? We know Z is Gaussian, so they together is jointly Gaussian, right? Sorry, I shouldn't write this. I should write more x and y, this pair is jointly Gaussian because I put them at the vector is Gaussian. So I know by fact -2 is Gaussian. That's the most confusing part for many people. You just need to see it more times, then you get used to it. And you should follow my suggestion. You always read or explain to yourself, when y is this, x is still random. That randomness has a density. The density somehow is Gaussian. Does it make sense? I think it should be, okay? I'm repeating this many times. I think somehow it's necessary for many people. And then I will know that conditional mean is what I want to do this, will be unconditional mean plus correlation, covariance, x and y, and times how noisy that is, times the surprise term. Okay, that formula somehow you got. And I can tell you this guy, the mean is what? Unconditional mean is 1. This x, this is 1, right? Plus covariance of x, y, what is it? Covariance of x, y. Covariance of x is z1, right? Y is z2, z3. So it's 1 by 2. 1 by 2. So it's a covariance of z1, z2, which is 1, 2 is 1, right? And z1, z3 is 0. That's my covariance of x, y. You should be able to read this table or this matrix, extract any information you need. And times sigma y inverse. What is sigma y? It's a 2 by 2 matrix, is this part. This is my covariance of y with y. This part, right? So that will be 4118 inverse times y is the surprise term, 2, minus the mean, which is 2 and 3. Are you with me? Okay, so it's 1 plus, I will say this is my favorite word, some number, okay? You can compute. It doesn't add any value or knowledge to you if I calculate this for you, right? You can compute the inverse. That will be some number. That number means the conditional mean, also means the minimum mean squared estimate of x given y. I think we're about time. So, but I want to point out, you can also find it out by conditional density. Conditional density. Sorry. Let me restate this sentence. I can also find, we can find the exact conditional density of x given y, small x given small y. Because this will be what? 1 divided by square root of square root this, e to the something, right? divided by x minus mu divided by sigma squared. Because this some number a will be my mu here. Okay, and also need to find this, which is you can also find by conditional of this y equal to small y based on the formula we had on last slide, this guy. I think you know all of these numbers. And sorry, let me just finish this within 30 seconds. So that will be sigma x minus sigma xy, sigma y inverse, sigma yx, which is 2 minus 1, 0 times 4, 1, 1, 8 inverse times 1, 0. Okay, this is some number b. And this b will be this with its sigma squared. Okay, so if I find this mu x given y, find sigma x given y, I know I can write down the density if you need, but typically don't. All right.